Hi there, I'm Ling. I'm a software engineer, hobbyist game developer, and recent graduate from the University of Chicago. This month's video is brief because I've just moved to a new city and started my first software engineering role after college, but I promise next month I will come back with a detailed video on graph traversal, including how I applied graph traversal to developing one of my game algorithms. In today's coding interview crash course, we're going to cover tree traversal. I will demonstrate 4 templates that we can use to traverse a tree. They are pre-order traversal, also known as depth-first search if we think of the tree as a graph, post-order traversal, in-order traversal, and lastly, level-order traversal, which is also known as breadth-first search if we consider the tree as a graph. These tree traversal techniques can be applied to either binary trees or N-ary trees. For each of the traversal technique, except for level order, we will also cover both the iterative and the recursive approach. First, let's look at how these traversal techniques compare and what tasks they are suitable for. So here's an example binary tree. Note that it's not necessarily a binary search tree because we don't need to assume any ordering among the nodes. First, we'll look at pre-order traversal. In pre-order traversal, we explore the roots before the leaves. Given this tree here, the pre-order traversal result will be 1, 2, 4, 5, and 3. Pre-order traversal is also known as depth-first search because, as you can see, we go all the way to the leftmost node before visiting any of the nodes on the right, 1, 2, 4. So we prioritize depth in our search. Because of this nature, pre-order traversal is good for copying a tree. Next, we have post-order traversal. Post-order traversal does the opposite of pre-order traversal. We explore the leaves before the roots. Given this tree, the post-order traversal result will be 4, 5, 2, 3, and 1. Next, we have in-order traversal. In in-order traversal, we visit everything in the left subtree before the right subtree. The in-order traversal result will be 4, 2, 5, 1, and 3. In a binary search tree, like the one shown below, in-order traversal will give the nodes in a sorted order from the smallest to the largest. In-order traversal will give -4, 2, 3, 5, and finally 18. Like we had 4, 2, 5, 1, 3, the ordering here. Because of this nature, in-order traversal is good for flattening a tree into an array. Finally, we have level order traversal. In level order traversal, we visit all the nodes of the same depth before moving on to those of the next depth. Given this tree, the level order traversal result will be 1, 2, 3, and 4 and 5, and 3's children if 3 had any children. Level order traversal is also known as breadth first search because if we take the root to be the starting node in a graph search, we explore nodes on the next level, i.e. the starting node's immediate neighbor, one step away, before moving on to the neighbor farther away. This is the basic concept of tree traversal techniques. Next, we will dive into LeetCode to see those techniques in action. For each of these techniques, we will first look at how to implement them recursively because it's more intuitive, and then we will explore the iterative solutions. So here we are on LeetCode, and this problem is precisely about binary tree pre-order traversal. Given the root, we want to return the pre-order traversal of its node's value. So for this tree, we want to output 1, 2, and 3. The solution is pretty straightforward with a recursive approach. If the root is none, we return an empty list. Else, we return the root first, concatenate this list by pre-order traversal of the left subtree and the pre-order traversal of the right subtree. Alright, let's run the code. And we passed the first test case. Let's submit our solution. And our solution is accepted. Cool, you can see the recursive solution is pretty straightforward. Next, we have post-order traversal. We'll follow the same recipe here. If not root, return an empty list. Else, because we want to make sure to visit all the leaves before visiting the roots, we return self.post order traversal of the left subtree plus self.post order traversal of the right subtree plus the value of the current node. Let's run the code. Alright, let's submit our solution. Cool, our solution is accepted. Next, let's tackle in-order traversal. If the root is null, we return the empty list. Else, we return self.inOrder traversal of the left subtree with the value of the current node sandwiched between. Concatenate with self.inOrder traversal of the right subtree. Now we run the code. And we submit our solution. Great! This is how we accomplish these 3 styles of traversal in a recursive fashion. Next, we'll tackle the iterative version. Now, for the iterative solutions, let's first tackle pre-order traversal. So first, we still check if there isn't a root. We return an empty list, and we make an array to record our return values, and also use a stack to keep track of nodes that we are going to visit. So while there is something in the stack, we pop the node off the stack. This will be the last item from the stack. And we append this node's value to our return array. If the node has a right subtree, we append it to the stack. If the node has a left subtree, we also append dot to the stack. We first check and append the right subtree before we check and append the left subtree, because append always append to the end, and we're always popping off from the end, so we want to make sure that we visit the left subtree first. And we're all done. We are good to return the return values. Let's run the code. Cool. Recall that the problem wants us to do pre-order traversal. And submit. And we're all set. I'm going to copy-paste this part into the post-order traversal solution so we can see how a small tweak to this template will determine whether we visit the leaves first or the roots first. So here, instead of appending to the return array, we want to prepend to it. So from collections, we import deck. I will make a future video on how this collections module come in handy in coding interviews. A deck is a double-ended queue, meaning that we can either prepend to it or append to it. We can also pop from the left or pop from the right. So here's our deck, and we need to change some more things about this template. So here we do append left because, if you recall, post-order traversal requires that we explore the leaves before the roots. So here we just popped off a leaf node from the stack, and we want to make sure that its value shows up first in our return array. And down here, we want to switch up the order of these two blocks. So we want to append the left subtree to the stack first, and then append the right subtree. And we run the code. And now we move on to in-order traversal. If not root, we just return an empty list. And this time we just use an empty list for the return and not a deck. And we have a stack that is initially empty. This is different from pre-order and post-order, where our stack contains the root. And we'll see in a second why this is the case. So while our root is not none, or we have something in the stack, while our root is not none, remember that we want to go to the leftmost node first, so we need to go all the way to the left. So while the root is not none, we mark the node as something that we need to visit by appending it to the stack. Then we set root to root.left because we want to go all the way down the left subtree. If we reach the end of this while loop, that means that we are already at the leftmost node of the subtree. At this point, we can pop off the root from the stack and append its value to the return, because this is the leftmost node. And because we processed the one on the left, we are now ready to visit the one on the right. So root is equal to root dot right. And when we complete both for loops, meaning that there's nothing more in the stack to visit, we return red. Well, you might think why we cannot just use stack here and ignore this part. Well, that's because the stack is initially empty if we don't have an initial condition where the root is not null. Our code will never enter this while loop. I know this looks a lot different from pre-order and post-order traversal, but this is how this iterative version works. Just like that, we tackled pre-order, post-order, and in-order traversal, both in a recursive and an iterative fashion. Next, we will cover level order traversal, which is also known as BFS, breadth first search. Now we're on LeetCode binary tree level order traversal, and we need to note that this return format is different from the previous 3 questions because LeetCode wants us to return a nested array with the first element being the node on the first level, the second element being the nodes on the second level, and the third element being the nodes on the third level, so on and so forth. Great, now let's see how to tackle this breadth first search. If not root, we return an empty list. Our return value is initially just an empty list. And again, here we need to, from collections, import deck. This time, instead of a stack, we are going to use a queue. And we will put root as the element of the queue. So while we have a non-empty queue, we are going to record our return row by row. So the return row, which is this nested list here, is initially going to be empty. And here we use a for loop. We are iterating over something that has a fixed size for this current level. That's why we are passing in the length of the queue. So here we pop off the first element of the queue and append it to our current level return. If the node has a left subtree, we append that to the queue. Note that this will not change the length of the queue up here because we are still inside this for loop. So this part is fixed. And we do the same thing for the right subtree. And after completing this for loop here, our red row is completely populated with all the nodes belonging to the current level. So we append it to the return. And Down here, we return ret. Let's run the code. This completes our template demonstrations for binary trees. Next, we'll look at how we can apply the same templates to N-ary trees, meaning that the tree doesn't have a fixed number of children. Here we are on LeetCode's N-ary tree versions. LeetCode has a follow-up question that says, recursive solution is trivial, can you do it iteratively? Of course, we're going to do it iteratively as we just did for binary trees. So I'm going to copy this over. And now each node no longer has a left and a right. Instead, it has a list of children. Down here, note that we are appending the rightmost subtree and then the leftmost subtree. So we need to iterate through those children in a reverse fashion and append them to our stack. So this is just a shorthand we use to reverse the list of children. Stack.append child. Remove these parts. This is it for N-ary tree pre-order traversal. Let's look at post-order traversal next. Again, the iterative solution is also pretty trivial given our work on the binary tree. So here, note that we are appending the children in order. So we just do for child in node.children stack.append child. And we're all done. For some reason, LeetCode doesn't have an in-order traversal problem for N-ary tree, so we will just move on to level order traversal. We grab the code for level order traversal, paste it here, and here we are appending the nodes again in order. So we do for child in self.children without having to reverse the children. Q.append child. And this concludes our template discussion on N-ary trees and also this crash course. I hope you enjoyed this video, and for more content like this, please subscribe to my YouTube channel, Lean Dev Lab, and I will see you in the next one.